Number 11. Here's a multi-parter. Nicotine has the formula CXHYNZ. So here we don't know what the ratios are. We just know that there's carbon, hydrogen, and nitrogen. To determine its composition, a sample is burned in excess oxygen to produce the following results. Now, we haven't gone over this, but one of the ways that you can attempt to determine the molecular formula for especially hydrocarbons, right? Hydrocarbons, is you can burn them because the products are very, very predictable, and it's very easy to isolate the different compounds that are products. But we get these following results. We get 1 mole of carbon dioxide, 0.7 moles of water, and 0.2 moles of nitrogen dioxide. These are the results at the end of burning, combusting, rapid oxidation. So we assume that all the atoms in nicotine are present in the results, meaning every single carbon, every single hydrogen, every single nitrogen that was in the sample is in here. None of it was left or lost, not actually burnt. We're assuming that 100% of it was burnt and became products. So let's start with A. Determine the number of moles of carbon present in the products of this combustion. Well, remember, these are the products, okay, producing the following results. These are the products. Determine the number of moles of carbon present in the products. Well, this is the only substance right here, the only product that contains carbon, CO2, and there's 1 mole of it. And we see that for every 1 mole of carbon dioxide, there's 1 mole of carbon, right? This is subscript 1. So there's 1 mole of carbon present in the products of this combustion. But see, note there's no carbon in the other substances. So we'll keep that in mind as we move forward. Go this way. So look at B. Determine the number of moles of hydrogen present in the combustion products. Well, here I've copied down our products again. And we see that there's hydrogen present in the water, that is a product, and there's 0.7 moles of water. But see this subscript 2? That means for every 1 mole of water, there are 2 moles of hydrogen. So we're going to have to apply this subscript 2 to the mole value that we have. We're going to go 2 times 0.7 moles to get 1.4 moles of hydrogen, and that's our answer for B. Move on to C. Determine the number of moles of nitrogen present in the combustion products. So same question, but we're talking about nitrogen here. Nitrogen is only present in this last product right here, NO2, and it occurs at a 1-to-1 ratio. For every 1 mole of this substance, there's 1 mole of nitrogen, right? This subscript 1 right here, and there are 0.2 moles of it. So for nitrogen, there's 0.2 moles of nitrogen in these products. D. Determine the empirical formula of nicotine based on your calculations. Well, we have 1 mole of carbon, 1.4 moles of nitrogen, and 0.2 moles of nitrogen. Right? These are the values that we just calculated in A, B, and C. What we just did. And so we have mole values for each of the elements present in nicotine. Much the same way that we have values of mole values for each element present in a compound when we start with percent composition. Here in this problem, we've just got to this point a different way. You realize we have the same type of information now. So from this point, we will take the same step, which is to identify the smallest mole value present, which out of these 3, it's 0.2. We'll divide all 3 values by 0.2. So obviously, the ratio for nitrogen is going to be 1. 1.4 divided by 0.2 is 7. 1 divided by 0.2 is 5. So our ratio of carbon to hydrogen to nitrogen is 5 to 7 to 1. So our empirical formula for nicotine is going to be C5H7N. Let's finish up with E. In a separate experiment, not the same one, in a separate experiment, the molar mass of nicotine is found to be somewhere between 150 and 180 grams per mole. Now, we don't know what type of exactness we have. We don't know what this experiment is. We just know that there's a window that the mass needs to fall under. we're being asked to calculate the molar mass of nicotine to the nearest gram. So we do have the empirical formula of nicotine, right? It's C5H7N1, right? N. And we need the mass of the empirical formula. So we multiply the number of atoms by their respective molar masses, add them all together, we get 81.1153. Now, with the appropriate number of significant figures, we'd have 81.12 grams per mole. And what we're going to do is we're going to guess and check. Okay, I know that 81.12 is not the appropriate molar mass because it's not between 150 and 180. And so I can multiply this by 2, just as a guess and check, right? Going from 1 to 2 to 3 to 4 to 5. And I see that this mass multiplied by 2 is 162. And I can see that 162 is in fact between 150 and 180 grams per mole. And so 2 must be the appropriate multiplier to get from the empirical formula to the molecular formula. But we're not being asked for the molecular formula, we're being asked to calculate the molar mass of nicotine to the nearest gram. Well, we multiplied by 2 to get 162.24. The other thing I want to point out is the question asks us for the nearest gram, so we'll round to this spot right here, and we'll stick with 162 grams per mole.